So linear, this would be now we start the discussion of the next chapter by talking about the linear independence, basis, and dimensions, and all the body of the work that we are going to discuss in this chapter. It is equivalent to some degree with the concept of range that we have mentioned in chapter 4, at least, where with the range, if you remember, we used to try to determine whether a specific vector is in the range of a set of other vectors. So if you remember, let me write here, so the concept of range was trying to identify whether column 1, column 2, and column 3 can define a range which might include another column 4. So the question was this: is column 4 in the range of this matrix? Let's consider this one matrix C, in the range of matrix C. This was the type of question we used to ask when we covered the ranges of a specific matrix. And now we are going to see this one in a more formalized way by discussing the linear dependence and linear independence. Now, with the definition of a linear dependence and linear independence, we first start by reporting the following definition, which will be as follows. So let's say, given set of vectors, v1, v2, vk, okay, then the vector equation, so let's write it this way, the vector equation, which is represented by alpha 1 v1 plus alpha 2 v2 plus alpha k vk, this equation, which would be equal to 0, has a trivial solution. So we have this equation, and these vectors, they are a given, okay? But this equation, and with vector equation, the question is, whenever we are given a set of vectors v1 to vk, this equation should have something which is unknown, which in this case, this would be the unknown parameter, right? So the alpha I. So if alpha I is the unknown parameter, we have several of these. This is equivalent to asking the following question: what is alpha? What is the solution vector alpha? Which means that if we have three vectors, we're looking for alpha 1, alpha 2, and alpha 3. We're looking for a vector composed of a triplet of numbers. And we say that this vector equation, which appears here, has a trivial solution. Then v1, v2, vk, these are linearly independent. Okay, so, and with trivial solution, we mean the following. This alpha vector is equal to 0 vector. So this is what the trivial solution means. Or we can also report it like this: alpha 1, alpha 2, alpha k. All of these parameters with which we are going to multiply all the given vectors vi, these should be equal to 0, 0, and 0. And now, for example, let's see. Now this is linearly independent. We can also give the other definition, which would be the following. If the solution alpha, vector alpha, is different from 0, okay, so if we can write this equation, and this is equal to 0 for coefficients alpha 1, alpha 2, up to alpha k different from 0, this implies that the vectors that were given are linearly dependent. Okay, so this is the definition of linearly dependent and linearly independent. For example, let's see. Let's assume if we have three vectors, they can be vector A, B, C. If these three vectors are not in a plane, what can we say about these vectors? So we have three vectors, they are not in a plane. Are these linearly dependent or independent? How could you answer this? So the question, so we have three vectors, and let's say the whiteboard is a plane. So we have vector A. Okay.
They're independent.
They are independent, right? Okay, yes. That's correct. So we have vector A, B, which are in a plane. So these would be independent, as you correctly said. These are independent. Now, if we have three vectors which are in a plane, then what can you say about these three vectors? They are dependent with respect to each other. Okay, so they are dependent vectors because it can look something like this. We have a vector A, we have a vector B, and then we can have also another vector C, which looks like this. Okay, now vector C. So let's assume that this vector C, if we bring somewhere here, it is going to match, it's going to be somewhere in here. So it would be that C, it is A plus B. In this case, we also try to draw this one to scale as much as possible. In this case, we could say the following. For which alpha 1, alpha 2, and alpha 3 do we get a 0? So in this case, we can have 1 times A plus 1 times B minus 1 times C. This is really equal to 0. Because A plus B is C, then minus C, these are vectors, okay? Minus C would give us so this is A plus B, but minus C is a vector which is going to point in this direction. So this A plus B and minus C for sure is going to give us 0. So what was the solution vector here? Alpha, in this case, was equal to 1, 1, minus 1. So for this triplet combination of alphas, we get these three vectors that are linearly dependent. Now, let's ask, what about these pairs? So if we have 1, 0 and 0, 1, are these linearly dependent or independent? How would you comment on this one? Dependent or independent?
Independent.
These are independent because if we multiply with the coefficient C1 times 1, 0 plus C2 times 0, 1, this is equal to 0, 0 only when this is 0, 0 only when C1 is equal to C2 is equal to 0. Okay. So this means that these are independent because this equation, which looks like this equation which we presented initially, this is satisfied only when all of these alphas or these coefficients C1, C2, etc., when all of them are all zeros. Okay, so they are independent. let's see. Let's give another, we can offer another example. What about this other vector, which is 1, 0, and 0.001? This set of vectors, it's a set of independent. These are also independent because for the same argument as we put in here. And then, what about this question? If we have vectors such as AB, CD, and EF. So we have three vectors, and these are in R squared. Are these linearly dependent or independent?
Dependent. They're dependent.
Did you say dependent or independent? Sorry?
They're dependent because they are in R2.
That's correct. Okay, I could not pick up what you said. Sorry. So they are dependent. That's true because they are in R2, and in R2, any two vectors they can form a matrix, and whose range is going to cover all the possible combinations of any pair of numbers. So that's true for three vectors which are in R squared. They should be dependent. They are dependent set of vectors. Okay. For the reason that E and F can be expressed as a linear combination of the first two vectors, and that is for sure. This means that that constitutes the linear dependence. Similarly, four vectors in three-dimensional space, if they are random vectors, they are expected to be, they are always dependent. Okay? So five vectors in four-dimensional space, they are still linearly dependent, but this is almost a little easier to intuitively accept. So this is, yeah, I think based on that argument put there, we can move to another definition. So in this other definition, we can say that any set of n vectors, so we have n vectors in Rn are linearly dependent if what? So let's see, when do they have to be linearly dependent? So these vectors, we have n vectors in Rn, and this will be the case if n is larger, or let's say larger than n. Let's try to read this from here. So we have three vectors. We have three vectors V, and they are in R squared. So we're just looking at this one. So in this case, our n is equal to 3, and n is equal to 2. So apparently, whenever n is larger than the dimension of the space, then we get those as being linearly dependent. So that's a good sentence which might intuitively bring us to senses better, which is the following. So if you have more vectors than the dimension of the space, then these vectors should be linearly dependent with respect to each other. Okay, this is now regarding. So let's see this another example. So if we have a vector 1, 2, 3, 2, 1, 5, so here we have three vectors, and the question is, are they dependent? or independent.
Dependent.
Dependent? Okay.
Yes.
Why?
Because if we multiply the first vector by 2
Yes.
plus the second vector, it equals the third vector.
That is correct, okay? So these are dependent and not independent, so this is true, because for this combination, we obtain, we get this relationship, or we could say that the vector C, which is equal to C1, C2, and C3, sorry, let's call this alphas, because I call the C as columns. Let's call this now alpha. So for alpha vector, which is equal to alpha 1, alpha 2, and alpha 3, this will be equal to 2, 1, minus 1. So for such an alpha, we obtain a homogeneous linear equation. What is a homogeneous linear equation? Is the addition is something like this. A alpha, this is equal to 0. So this is what we used to call, or we still call, the homogeneous equation, which means that this is different from AX is equal to B, right? Okay, let's see another corollary here. So if we have two vectors are linearly dependent, what can we say here? We can say that if two vectors are linearly dependent, then one of them is scalar multiple of the other. Of the other vector, okay? So with regard to this one, let's assume for a moment that we have a vector which is 2 minus 1, 3. So if this is a single vector, how can we make up another vector which is linearly dependent to this? We just multiply this one by minus 1, we get minus 2, 1, minus 3. This is linearly dependent. Also, we can multiply them by 3, so this would be 6 minus 3, 9. These are linearly dependent with respect to this, but also linearly dependent with respect to this one. It is obvious because apparently they are scalar multiples of one another. So in this case, in order to distinguish whether two vectors are linearly dependent or not, what we could, so for example, let's try the following. If we have here 8, A and B, so if A and B is linearly dependent with this vector, the question could be, what is A and B? What we can try then to do is 8 over 2. This should be equal to A over minus 1, and this would be equal to B over 3, which means that the ratio of these two vectors should be a constant value. And from here, we can easily conclude that the A, let's write the solution for A. What is A? A is going to be, it's 4. So we get minus 4 divided minus 1. And this is equal to 12 divided by 3. So A and B, here we have them, okay? Then, and similarly, so it looks like, let's write these numbers that we just found out here. So we have 8, minus 4, and 12. So these all are linearly dependent to this number, but how can we make up a vector which is not linearly dependent with this initial one? So what we could do, we are sure that we can destroy the linearly dependence by just changing one of these numbers by some value, okay? So any set of numbers which are not linearly dependent, we can make them like this. We can say 8 minus 4, 12 plus k, okay? Or similarly, 8 minus 4 plus k, 12. So if we change only one of the numbers by some non-zero value k, this will all be linearly independent with respect to this, okay? And this set of vectors that we wrote here, they are all dependent for reasons that we provided so far enough. Okay, so then okay, so here we have, I believe we all remember the definition of a space and subspace, right? What was a key element when we were trying to determine if some space was the subspace of some other space? So how would spaces be subspaces of each other? We used to search for one essential element, which was the possibility of that space having the zero included or not, okay? So we used to say that if you have a space which could be a plane, if this plane is not passing through the origin, we used to say that this plane, for example, is not the subspace of R squared or R cubed probably, because planes, they are element of, so we find them in R cubed, but then if this plane is not, so if this one, if it is including the zero, if this includes the zero vector, then this is a subspace, okay? Is a subspace. So we remember this from the discussion of spaces and subspaces, and regarding this, we can say that we can construct a theorem which says that a non-empty set of vectors which includes zero which includes the zero vector, then this one we call linearly dependent. So this vector space, it's a linearly so this is something we can add. I believe we can erase this part. For example, let's assume these three vectors, 1, 2, 1 minus 1, and 2 minus 5. So the question is, are these three vectors linearly dependent? We know this one very well so far. We know that since all of these are pairs of numbers, which means that these are in R squared. So all of these, they are elements or vectors in R squared. But we have three of these. That means that these are linearly dependent. But now, just as also to remind what we did in the previous sessions, how would we determine the linearly dependence of these? We can formulate the question as follows. We can say A times X. This would be equal to 0. And then we can try to solve for X, right? And how can we pose this problem then? This problem, we can pose it like this. The coefficient matrix is going to be 1, 2, 1 minus 1, 2 minus 5. So this is the matrix. What is the dimension of this matrix? This is 2 by 3. And then we have to multiply here with a vector which should be 3 by 1. Or am I right? Yes. Yes, that's true. So this would be x1, x2, and x3. And here we should get an answer, which should be, what is the dimension here? Thank you for 2 by 1. So we get here 2 by 1, which should be 0, 0. And now this is how we write this in a complete form. But in order to solve it, we construct the augmented matrix, which we have 1 minus 1, 2 minus 5. We augment this one with the vector, the answer vector, which is the what? The 0, 0, okay. And what is the next step to solve this system? We try to obtain, or we try to get the reduced row echelon form. And when we try to get the reduced row echelon form, we know that we are going to combine linear combinations of the first row with the second row, because this is all we have. And in this case, we know very well that this column is 0, 0. So even if we multiply that with constant numbers, those zeros, they will not change. So that means that we'll have to work with only with this part, 1 minus 1, 2, 5. So we can get the reduced row echelon form of this augmented matrix here. But after we have stripped away the 0, 0 vector, and then if we apply a couple of operations, we obtain the following. We get 1, 0, 0, 1, and we should be able to obtain this identity matrix looking like part of the large matrix, because we always know how to obtain the leading ones, and we are also very good at making zeros in the columns where the leading ones exist. So then we get here minus 1 and 3. So this is a free variable. We know this is a free variable because the leading ones are here. So leading ones are here, this becomes a free variable. And with this free variable, what do we do here? We say that x3, in this case, we say x3 is equal to s. Okay, this would be our free variable in this case. And the general solution, we can obtain the following. We say that the solution x, this should be equal to x1, x2, x3, and all of these are a constant s. Since the third one was a free variable, this will be here 1, minus 3, and 1. Okay, so we get here a line that can satisfy this equation. Okay. Let's see. Okay, we have a couple of examples of x3. X3. Well, now, actually, when you talk about the linearly dependence and independence, it is always good to construct an equivalence with a function. So these principles that we are discussing right now, we can talk about the linearly dependence and independence of vectors, but at the same time, we can talk about the linear dependence and independence of functions, okay? So we can say here, these are equivalent to functions. So what we mean here is that we can ask the following question. So assume that we have function f1 is equal to 2x and the function f2 is equal to 10x. Are these two functions linearly dependent or independent? We say, how do you define that? We say the following, the definition. We say if we have c1 times f1 plus c2 times f2 equal to 0, if c1 and c2 is different from 0, so we do it this way. If c vector, which is equal to c1 and c2, if this is different from 0, then these functions, we say immediately, we say that functions are linearly dependent, right? What do you think in this case? Are these two functions dependent or independent?
Dependent.
They are dependent, that's true. They are dependent because we can linearly combine them, right? Which means that we just multiply them with scalar numbers, with scalars, and if we combine them, we can easily get a 0. So in this case, what would be the solution? The solution would be the following. So we can get C1 and C2, they can be equal to -5 and 1, okay? So this is a linear combination which can easily give to us a 0. Now, there is another way to look at this problem, is the following. We can take the ratio of these two functions. If it is a scalar, then we say that these are linearly dependent, okay? Which we said the same argument for vectors. What did we say? We had a vector which was 2, -1, 1, and we said, or whatever, what was this? This was like something like 3. We said that, how can we construct a vector which is linearly dependent to this? We said that we can multiply by 4, and this was linearly dependent because this was 8 minus 4, 12. Similarly, we have these two functions, which are 2x and 10x. So 2x and 10x. Are these two functions linearly dependent? We just take the ratio. So what did we do here? We took the ratio of this vector with these. Now we just do the following. 10x divided by 2x. This is a scalar number 5, okay? And this is what we do in the linear combinations. We multiply whatever we are given with constant values. So apparently these are dependent. Let's see another example. We can have f3 is equal to x, and the function f4 is equal to e to the power x. The same question remains. We can ask the same question. We say, are these two functions dependent or independent?
Independent.
Say it again.
Dependent.
Independent. Independent. Okay. You just say in. That's enough. Okay, because the rest it gets confused. So the question it remains the same. We say, can we have a constant c3 times f3 plus a constant c4 times the function f4 to be equal to 0? Yes, we can. But for which values of c we get a 0 here? The solution is only for c3 and c4, these two coefficients, only when they are both equal to 0. This is the only solution. So if this is the only case when it happens, we say that these two functions, they are linearly independent. So these two are linearly independent. Okay, and another example is the following. So let's assume we have function f5, which is equal to sine x, okay, and function f6, which is equal to x squared. Are these two functions dependent or independent? They are independent, okay? Now, we should not confuse the following. Now, f5, when x is equal to 0, what is f5? For x is equal to 0, so let's say is 0, that's correct. X, what is this other one?
0.
It's also 0. But we don't want these to become, we're not checking the linearly dependence for specific points. We're asking for the whole range of x. Okay, so x is from minus infinity to plus infinity, which means that we're putting a lot of constraints. So the only possibility which makes these linearly, when we check for linearly dependence or independence, we're checking for the whole range of the functions. Okay. Now, a very good example is, well, there are many examples, and I can offer quite a few, but one which is very interesting is the thing. Okay, so what we observe here, we have a relationship where we have the addition of three components, or we have two components which is equal to a third one, and we need to find a solution for this system. And in order, so here, this D, we can put this one actually X, so this is X, and this is X. But now, assuming that X is a real number, it can be any number, so X is from minus infinity to plus infinity. How can this equation be true? We can say the only possibility for this equation to always be true is that these exponents, they are all the same, okay? Because exponential terms, they are so scary, they increase so fast and they decrease so fast, so that it's hard to keep up. Then we simply say that this beta 1x, this is equal to beta 1x, and this would be equal to beta 2x, okay? So we can conclude some important relationships here, and we can also add the following. Then we can say also that this coefficient EI0 plus ER0, this would be equal to ET0, okay? So this is how we are forced to conclude these different. So we can use the idea of linearly independence to conclude such an answer, okay? Why? Because these functions, they are hardly linearly dependent, because their ratio is not a constant number, but it would be even, we can even pick a simpler example, which would be the following. We can have f7, this is equal to x, and f8, this is equal to x squared. Are these linearly dependent? Now, with these examples that we have on the board, we say that they are independent. First, because x squared divided by x is not a constant. This is equal to x, okay? Which is not a constant, because x changes a lot. And also, we know that the equation c7x plus c8x squared is equal to 0 only if c7 is equal to c8 is equal to 0, okay? So this is the linearly dependence and independence of functions. We can add in order so that you completely understand this one easily. Imagine e to the power x. We can have another function f10, which is e to the power, e to the power 2x. Most definitely, but these are also independent, this other pair of functions, and many more. Actually, often, I believe that when we discuss the linearly dependence and independence of vectors, considering also the case of for the functions, whether they are linearly dependent or independent, it provides a little more intuition, because you are going to become engineers very soon, and to some this might be more intuitive than the linearly dependence and independence of the vectors. Unless you work too much with vectors, and you might be prodigies of that. But if not, if it's not the case, the functions perspective, it might be a good approach. Okay, if you like, we can have a short break. Do you have any question for what we did so far?